here's something interesting to think about. This information that I have over here to the side, you'll recognize this. This is the problem we just did. But I got rid of the column for the tally and the column for the relative frequency, and all I have is just frequency here. It says, even though the visual display of frequency distribution is helpful in seeing the data tendencies, the original data is lost. A way to remedy this is to use a stem and leaf display. So what are they meaning by this statement? So let's look at you look at the histogram or the group frequency, and what they mean by the original data, they mean even it's lost here. Like, I don't know how many hours each person studied. I know 6 people, it fell between 10 and 19, but without looking at the original list of data, I don't know. I know 6 of them fell between 10 and 19, but I don't know what those values were. So, to focus on what those values were, we could create something called a stem and leaf plot. Okay, so we're going to present the study times data of example 2 in a stem and leaf display. And I'm just going to show it to you rather than building it right in front of you. Here it is. Now, what is this information? Okay, now remember, there were 6 people that said they studied between 10 and 19 hours. Well, look, this is those people. The one is the teens. So somebody studied for 18, somebody studied for 15, somebody studied for 12. You see where we're going with this? Where am I getting that 12 from? Make sure you're clear on this. So the 1 is the 1 in the teens, and then the 2 is the 1's place. So somebody studied for 12 hours. Somebody studied for 16 hours. Somebody studied for 14 hours, and somebody studied for 17 hours. And then, of course, when you go to the second row, I know you get it by now, somebody studied for 29, 26, 25, 24, 22, 29, 29, 23, 24. Okay? How does that help? Well, look, it's just like a histogram. Remember, most people studied in the 30s? Okay? That's your histogram right there. Notice how it's the longest. If I go back and look at the histogram, this is the study times. Remember, 30 to 39 was the longest, or it's the highest up here. And that's exactly when you do a stem and leaf. Look, that's like your histogram, but just turned on its side. So there's more in the 30s. Then the next amount was people studying in the 20s. And then the next amount was tied in the teens and in the 40s. And then you see in the 50s and the 60s, and then only one person studied in the 70s hours. So the stem and leaf display actually tells you a lot. It's like a histogram combined with all your information right in front of you. Okay, well, what about bar graphs, circle graphs, and line graphs? Well, frequency distribution of non-numerical observations can be presented in the form of a bar graph, which is similar to a histogram, except the rectangles or the bars usually are not touching. Remember, I mentioned that earlier. And sometimes are arranged horizontally rather than vertically. And you know, the stem and leaf plot is almost like, again, a histogram or a bar graph, but it's horizontal instead of vertical up and down like we had it before. So the bar graph in figure 5 shows the frequency of occurrence of the vowels A, E, I, O, and U. I want to show you to that in this particular paragraph. So somebody went and counted all the A's, all the E's, all the I's, you get it, all the O's, and all the U's. And there you go. So look, you notice how the bars are not touching each other? That makes this a bar graph, okay? And there were 30 A's, or a little over 30 A's. And then there's 30 something, I can't tell exactly where that is, E's. It looks like there's right at 20 I's, 24 maybe O's, and maybe right at 10 U's. So that's kind of neat, a neat problem, but that's again an example of a bar graph for you. It won't be the only one you see. Hold on just a minute. Here's a problem. Example 4 says a 2017 study by Swiss researchers predict a worldwide 2030 baseline of 200,000 tons of antibiotic use in food animals, with possible reductions if one or more of the following strategies were applied. So one of the strategies to apply was capping use at 50 milligrams per kilogram of animal product. So in other words, restricting the amount of antibiotics. or reducing consumption of meat to 165 grams per day per person. So that's saying you can only eat 165 grams per day. And then T, imposing a 50% tax on antibiotics. So all of these would be strategies to cut down antibiotic use in food animals. And so notice what we have a bar chart here. It says to the nearest percent, what reduction is predicted under each of the following intervention strategies. So let's see what we have. And I've got a bigger version of this, and I'll back and forth between the questions and the chart. So here's the chart for you. So they're saying if you don't do any intervention at all, you notice the estimated global antibiotic use in 2030 is 200,000 tons. It goes right up to 200,000. But if we use the C strategy, remember C represented capping use at 50 milligrams per kilogram of animal product, then 81,000 tons would be the antibiotic use. R was, if we remind ourselves, R is reducing consumption of meat. So if people don't eat as much meat, and it would reduce antibiotic usage to 157,000 tons. T was the taxes, and then it breaks it down. Well, what if we do R and T, or C and R? And then C, R, and T, obviously the best option would be to do them all, right? It would reduce antibiotics to 40,000 tons by 2030. So the goal is just to lower antibiotic use in food animals. So let's see if we can answer the questions. I'm going to skip back a page again. I'll be going back and forth. Okay, so the first question says, refer to the bar graph to the nearest percent what reduction is predicted under each of the following intervention strategies. So what reduction? This is how much, this is the usage. Notice at the bottom, so again, I'll make it big, estimated global antibiotic use. So how much reduction would we have? Well, none, right? It goes right up to 200,000. How could you just calculate that on paper? Well, you could say, 200,000. Again, I picked the pen, but it just didn't let me. Okay, so 200,000 minus, and we're going to leave off the thousand since this did, minus where it is, 200. But then we divide that by the total amount, which is 200. That's going to give you a percentage. So this is 0. Right? 0 on top divided by 200, so 0% reduction. If we don't do anything, then it's not going to reduce. So that's what they're trying to say there. Now I'm going to flip back to the previous page and look at this question. So the second question, B, is C only. If we cap use at 50 milligrams per kilogram of animal product, in other words, use less antibiotics and say you're not allowed to use any more than that, that would be C. So bigger here, C, notice it goes to 81. Now that's the use, not how much would we cut back. So if we calculate how much we would cut back, then we'll do exactly like we did the last problem. That would be 200. Me and this pen, we're going to get mad at each other. So 200 minus the 81. So that's how much we cut back. But I need to divide by 200 to get a percentage. Now we know 200 subtract 81 was what? 119 divided by 200. And then I'm just going to type that in my calculator, y'all. So 119 divided by 200 gives me 0.595. which is 59.5%. Okay, so a reduction in 59.5%, which is a pretty good reduction. All right, for the next question, I'm going to flip the page back. Now it asks for C only. So if you'll notice, C is at 81. And what does that mean? That's the estimated global antibiotics use in 2030. So they're saying 81,000 tons. Yes, 81,000 tons will be used in 2030 if they do C only, which is capping use at 50 milligrams per kilogram of animal product. So only using a certain amount of antibiotics. So how do we calculate it? This is going to be just like the last calculation. So again, let me make sure my pen is working properly. Now 81 is our number, right? So we're going to say 200,000 is what it would be, minus the 81 that it is if we cap our antibiotic use on animals, and then divide that by 200 to get the percentage out of 200. So 200 minus 81 gives me 119, and then divide that by 200, and that gives me 0.595. Move the decimal 2 places to the right, that'd be 59.5%. Now, depending on where you're asked to round, you could round that up to 60%. It just depends on where you are asked to round, and that was question B. Now, let's take a look at question C. And again, I'm going to flip the page on you. Now, question C says C and T. So I'm going to go back and look at my zoomed in graph here, my bar graph, and look for C and T. I see C, a CR, a CT. Now, I can't do C and T myself, but look, they have R and T together. They have C and R together, and CR and T. But no C and T. And again, there's no way I can look at C and T separately and determine that. I would have to know combined what effect that might have. And I just don't know because they didn't give us that information. So I was just going to say information not available. Info not available. We can't do that one. Okay? And let's look at question D. I'm flipping the page on you. Now D says CR and T. If you'll notice down here at the bottom in white, there is a CR and T. Let's zoom in on it. There it is. CR and T is 40. That's the one that has the maximum effect. Of course, if you do everything, you would think that would have the maximum effect, but it's certainly not necessarily. And so I'm going to do exactly what I did on the first ones. I'm going to take my 200,000, which is what it would be if we didn't do anything. I'm also going to see if I can get my pen to take effect. So 200,000 minus the 40. So that's a reduction in 160,000. And then I'm going to take that answer, 160 divided by 200, to get a percentage. And so 160 divided by 200 gives me 0.8 or 0.80, which is an 80% reduction. And of course, that is the biggest reduction out of all of the strategies, is to do everything and see if you can reduce antibiotic usage in animals. Now, to discuss some more visual displays of data, you know what a circle graph is. It says, or a pie chart is also a helpful way of displaying data. Remember, a circle is 360 degrees, so when dividing up the circle into pie pieces, you should take the frequency distribution percentage and multiply this times 360 degrees. So, you know, I could draw you a circle graph. I'm sure it's probably not going to be very successful, but here we go. There's my circle, and I'm trying to divide this up into parts, and let's just say, you know, you had a 72%. Let's just say we had a 72% frequency distribution. Then to figure out how much of the triangle I would shade in, I would take that 72%, 0.72 times 360 degrees, and that would tell me the degrees of my wedge or of my piece of pie. So 0.72 times 360, that gives me 259.2. That's in degrees. Now remember, 360 is all the way around. So 259.2 is pretty big. But you could use a protractor and find it, or you can, you know, kind of guess. I am calculating, by the way. I'm just sitting here typing on my calculator and not saying a word. because it's not doing what I want it to do. Probably because I'm typing wrong in it. But 259 degrees, and it leaves about 100 degrees. And so, listen, I'm going to do my best guess. That right there is about 259 degrees, and I would shade all of that. And that would be my piece of pie to represent 72%. You know, but we can do our best job. I just made that one up off the spot. Probably didn't do the best job. But let's see what we can do with this. Okay, so here's a problem. Example 5. Andre's investment advisor recommends the portfolio allocations shown in our table right here. Present this information in a circle graph. So again, stocks is 55%, bonds is 20%, cash is 15%, and metals is 10%. I really would have liked to seen them put percent all the way down. They didn't. And I guess that's just a given. If it shows up on the first one, then it's true for the rest of them, but that would make me feel a lot better. Now, how do I do this? Well, I would take my 55%, write it as 0.55, multiply that times 360 degrees, and it would tell me what kind of angle I need to put in there. So 0.55 times 360 would give me a 198 degree angle. 20%, 0.20 times 360 degrees. So you could do 0.2 times 360. That would give me a 72 degree angle. 0.15 times 360 is the next one. That would give me a 54 degree angle. And then 10%, or 0.10 times 360. I shouldn't need my calculator to do that. Would give me a 36 degree angle. So again, I'm changing these decimals to a percent times 360. Again, the 360 comes from the amount of degrees in one circle. Now, if I added all those up, they should add back to 360 as long as this is a complete frequency distribution. 55 plus 20 is 75, plus 15 is 90, plus 10, that's 100%. So yeah, that should add to be 360. Now, instead of drawing this circle myself and getting out my protractor, I'm using the book's version of that. But remember, 55% is 198 degrees, and that we would guess that's a 198 degree angle right there. 20% in green up there, remember, was 72 degrees, so that's a 72 degree angle. And then the 15% was a 54 degree angle, and then we have a 36 degree angle. So that's how you do a pie chart. Again, if you have a protractor, you can make it nearly perfect. If you don't, you have to do a lot of guessing, and that's no fun. So maybe we should get protractors for this class. Let's do one more problem in this section to wrap up visual displays of data. All right, so what you have here, notice, if you look at the visual display of data first, you have two separate line graphs. Now, this is different than a frequency polygon, and the fact that it doesn't come down and touch like the axis at the bottom. This doesn't connect all the way down. It's just a line graph, which takes a point, and in this case, notice across at the bottom is your years. So for each year, there is a point, but it's on two different graphs. You got the blue graph and the green graph. Now, the green graph reads resistance or partial resistance to ciprofloxacin. I don't know what that drug is. And then in blue, you have resistance to ceftriaxone. Again, I totally messed up those pronunciations. That's not my strong point, is pronouncing drugs. I don't know how to pronounce those, but we're not going to worry about it. We got the blue drug and the green drug. So let's talk about that. It says, what time frame is reflected in the figure? Now, you might not be able to see this very well, so I'm going to zoom in a little bit closer. There we go. Now, you might can see clearly what time frames we have going on here. So it starts at 1996, and then it goes to, it looks like 2011. It's not labeled. Notice it goes from 96 to 98 to 2000 to 2002, so it's skipping years. But look how these are closer together at the end. So I would say the answer to question A is from 1996 to 2011. Now let's look at what they ask us for question B. I'm going to change slides. Question B, in which years was resistance to ciprofloxacin? Hey, you think that might be right? Or ciprofloxacin, what about that? Anyway, Ciprofloxacin is the green one, okay? In which years was the green one greater than the blue one? That's all we're asking. So let's flip the screen and look at that. Green one greater than the blue one. Notice that the green one is greater than the blue one. Let me get my pen working. Let's go to red so we can see it. Look, in 1996, it's hard to see it, but the green is just a little higher than the blue. And then 1997, look, the green is higher than the blue. In 1998, the green is higher than the blue. Now look, in 1999, right here, the blue is higher. And then the blue is higher all the way until you get to, look, 2011, the green is once again higher than the blue. So if I list them, that's 1996, 97, 98. Now 99, it switched on us, so then we go to 2011. So that would answer that question. Okay, let's go look at the third question. Over this time span, what was the highest resistance to the one I don't know how to pronounce at all, ceftriaxone, achieved, and when did it occur? So over this time span, what was the highest resistance, and when did it occur? Now notice the chart gives us, I'm trying to see over here, the chart gives us resistance, and it asked about the blue one. So where is the blue the highest? If you'll notice, that's right up here. But that doesn't happen just one year, it happens 2 different years. So in 2002, and then right next to it, 2003, the one that's not labeled. So the years would be 2002 and 2003. Now, what's the actual resistance? So then you work yourself over here to the left, and it says percent resistance. So that would be 4.5% resistance. And that would answer question C. So I hope you have a good feel for all the different visual displays of data. We talked about a lot, but all these things I think you're familiar with. Remember the histogram, you have the rectangles that touch each other. Then you have a polygon or a frequency polygon where you label the frequency, but it looks just like a line graph right here, but it comes all the way down to the axis on the left and down to the axis on the right. And then you have bar graphs where you have rectangles that don't touch each other. They're often on their side. You have a stem and leaf plot. And then you have a circle graph, right? Or a pie chart, often called a pie chart when we're growing up. And then you have a line graph, and we just took an example comparing 2 different line graphs. So I hope that helps. If you have any questions, of course, let me know, and have a good day.